Hello and welcome to the 6th week of the Operations Research 1 course. So last week we've talked about this method called Big M to solve a LP problem. Now this week we are going to look at how we may identify an infeasible linear programming problem using the Big M method. And then also, if you remember last week, we've talked about some possibilities when we solve a linear programming problem. They are first, we may find a unique optimal solution. We may find that an LP has alternative optimal solutions. We may also find that the LP is unbounded. So now we're going to talk about the fourth possibility, which is the LP is infeasible. So let's start. Okay, so here's an example, which is the modification of the Bevco example that we've seen last week. As usual, what you need to do is first you check if there is any right-hand side that is negative. Here, there's no such thing, so you can proceed to transform this problem into a standard form by adding slack variable or minus excess variable. And then you add artificial variable where you have the excess, and then you add artificial variable again because the third constraint is an equality, and here you don't have any variable that can be a basic variable. And then you know that when we want to do the Big M method, you need to penalize all the artificial variables that appear on your model. So because this is a minimization problem, so in row 0, you will have m times a2 and then m times a3. Notice that the signs here becomes negative because this is the row 0 form, which means that we put all the variables into the left-hand side. If these are all in the left-hand side, the sign of the penalty would be plus m times a2 plus m times a3. Again, this is minus because we put this in the row 0 form, so everything is on the left-hand side. So this is the model that we've got so far. And then if we put that into a table, we see that we do not have a canonical form, so that this is not a BFS. What we need to do is that we need to eliminate this minus m from, let me highlight them. So we need to eliminate this 2 from the row 0 such that the result would look like this. This is a canonical form in which the basic variables are S1, A2, and A3. This is what you've seen before, right? And then how to eliminate these two coefficients from row 0, you need to do this, the old row 0 plus m times row 2 plus m times row 3, and then sum everything, sum all these three equations, you will obtain the new row 0 that you write down here. So the last table on the previous slide, we have already got a BFS from the table because each row has got a basic variable. So, and then you can see it's in a canonical form. So this is already a BFS. Okay, so let's proceed as usual. This problem is a minimization problem. So we pick the variable in row 0 whose coefficient is the most positive. We perform a ratio test, pick the smallest, and got the intersection as the pivot. And then we perform arrows such that this column x2, I think there's a typo in the title, this should be x2. So that column should be having the value 1 in the pivot position and then 0 in all other positions. Now looking at the table again, the BFS on the bottom table, you see that for the minimization problem, this table looks already optimal because in row 0 you do not see any coefficient that is positive. So this table is already optimal from the point of view of minimization. However, you notice that there is an artificial variable that shows up in the optimal table. which means that in your final solution, in your optimal solution, you still have something artificial that shows up in your solution. Remember that artificial variables, they represent something that does not exist in the real world. So it means that in your optimal solution here, you propose something that actually does not have any existence in this physical world. So it means that this problem is an infeasible linear programming, because after you try to solve it up to the point where the BFS looks optimal, you still have an artificial variable that has a positive value in the optimal table, which is A2. So this is the sign where you can say that the linear programming problem that you have is infeasible. Okay, so here's a question to check your understanding. Given a table of a BFS here, and then you are told that this problem is a minimization problem, the statement is that the BFS in the table shows that the problem is infeasible because there is at least one artificial variable with positive value as a basic variable. Is this statement true or false when you are given the BFS on the table? I will give you the answer after the pause on the video. The answer is false. We can say a problem is infeasible if any artificial variable is positive in the optimal table. So this word is very important. You can only say that an artificial variable appears as the basic variable and then the problem is not feasible or the problem is infeasible only when you have optimal table. Then you can draw that conclusion. This table or this BFS is not optimal yet because in the case of minimization, you still have a variable with positive coefficient. So you should keep doing the simplex iteration until you reach the optimality on the BFS, and then you check whether there is any artificial in the basic variable. If that is the case, then you can say the problem is infeasible. But at this point, at this table or at this BFS, you cannot draw such conclusion. Okay, so that's the end of this video to show you how we may identify infeasible linear programming using Big M method. On the next video, I'm going to talk about another method which we can also use to solve a linear programming problem that is called two-phase simplex method. So see you on the next one. Thank you.